Okay, so this is 420 hydrogeology, and this is a supplemental lecture on infiltration and unsaturated flow uh, and how it leads to recharge. So we're going to talk about flow in the unsaturated zone, and so let's think about a cross section of the unsaturated zone. So here's my let me try and draw that a little better. So here's my land surface. And going down, here's depth. And I'm gonna plot. There's a little tree to put it on our land, so we know this is the top here. And I want to plot the volumetric water content in our soil. And down here at some depth Z is my water table. And just above it is the capillary fringe, the height of fairly saturated water pulled up by capillarity. And my volumetric water content is going to vary between here. This will be theta sub r, the residual water content, and n, the porosity. And we're going to start off at T0, which is a long time since a precipitation event. So a long time from the last precip event. And in this state, our soil is really well drained. And because we got plants and trees up here in the surface, sucking with roots that are sucking the water out, right? We're going to be drier at the surface, and we're going to get wetter as we go towards the water table. So T0, our profile of volumetric water content might start out here pretty close to the residual water content, increase gradually as we got close to the water table, and then hit the fully saturated conditions here at the capillary fringe and below. All right. So this is T0. Now, now let's think about, we get some precipitation. All right. And so water falls at the surface. All right. So we're getting water at the surface, and it's starting to infiltrate the soil. So times T1. Let's make these blue. So T1 and T2, we have infiltration of this water, all right, as it seeps into the soil surface. So what'll happen is the soil will wet up at the top, all right, and we'll get a front. So let's call this T1. And this T2, where we have increasingly saturated water near the top, all right, T1 and T2, where the water, so the water is infiltrating, we have increased saturation at the top. All right, so this is our precipitation time. Precip and just after. So this is during the event and just after. Now, after the event, we've got all this water and it's going to drain and drain down into our soil profile, and we call that redistribution. So let's call T3 and T4 redistribution. All right, and during T3 and T4, this wet portion starts to drain, and we move our front of increased water saturation down. So T3 might look something like this, all right? And T4 might look something like this. So our front of increased saturation has moved down into the profile, and the wet surface zone is starting to dry back up as water drains. And this is called redistribution, all right? The draining of this wetting front down and increased water moving down. All right, finally, we have drainage, all right? And that's where we sort of return back to our all right, we return back to our dried profile. So at T5, we might see something like this. And at T6, we're starting to drain pretty close back to our original profile. So this is T5 and now T6. All right, so we've ended up back at our original profile. And these times are past the precip. All right, so during precip, we wet up from the top, and then we drain, we redistribute, and then drain back to our sort of long-term profile between precip events. So one thing, this portion of water that makes it past the root zone and drains to the water table becomes recharge. Ah. All right, and the water that moves into the soil is the infiltration. All right, and infiltration and recharge are not equivalent because roots down here are transpiring water and taking water out of the system and putting it back into the atmosphere. So infiltration minus transpiration would give us recharge. All right. So for us, it's pretty important to understand how much infiltration we might have. And recall that the relative conductivity, or and in turn the effective conductivity of our soil, and the pressure head of our soil all change as a function of our saturation, right? So the more saturated we have, the less pressure head or capillary pressure we have. So the more saturated we are, the lower the negative capillary pressure, and the less water we have, the lower the effective hydraulic conductivity. So those two processes, when we look at our profile, mean that we're going to infiltrate water at different rates. So at the beginning here, we start off at very low saturations. We have water up here. So we have really high tensions, and the water will want to get pulled in. But we also have very low hydraulic conductivities. As we increase our saturation up here, we come to a saturated state, and so our water tension and our effective hydraulic conductivity sort of converge to saturated parameters. And this leads to a time variable infiltration rate. Now, there's a lot of different ways to try and calculate this infiltration rate, but one way that's commonly done is called the green Ampt function. And the green Ampt function, it approximates the time variable infiltration rate. And here we'll call it Q sub I. All right, for the infiltration flux. And what the green Ampt function says is that the infiltration flux Q sub I is equal to square root of 2 over 2 tau to the minus 1/2 plus 2/3 minus square root 2 over 6 tau to the 1/2 plus 1 over square root 2, 3 tau times Ks. All right, and let's define all these variables. So tau is some measure of time. It's a dimensionless time, and it is the time since infiltration started. So this is during the precipitation event, and assuming sort of a constant precipitation rate. So the time since infiltration started and I should say that the way the green Ampt assumes infiltration is occurring is that there is some ponded water height here. So if we rain for long enough, we build up a layer of ponded water. And H sub F is the height of that ponded water. Oh, sorry, H sub S is the ponded water height. So let me write a few more things out. So chi here is the H sub S minus H sub F. So chi is this ratio. All right. H sub S is the ponded water height. All right, that's this height here. After we rain, we say, oh, look, we got this much water ponded on the top of our surface. That's driving the water to infiltrate down into our soil, and H sub S is the height. H sub F is down here at the wetting front. So we call this area the location of the unsaturated zone that is seeing increased moisture from the infiltration rate. That's the wetting front. And H sub F is the capillary pressure at the wetting front. That's the negative of the pressure head at the wetting front. Let's see, theta sub S is the saturated volumetric water content. This is equal to the porosity. Should just be porosity here, but theta sub S is the saturated volumetric water content. It's equal to porosity. Theta sub naught is equal to the initial water content before infiltration begins. So in our scenario up here, it would have been theta sub R. Our infiltration started, we were at theta sub R, all right? But we could have had another rain event here at time 3 and we wouldn't have been drained all the way back to theta sub R, for example. So this is the initial water content in the surface before infiltration begins. Now, our capillary pressure at the wetting front is, again, a function of the saturation. And we can estimate that by saying, let's actually, before we get there, let's define the rest of our terms. So here we have tau, and we have, it's a function of this psi, tau, and then the other one we need to define here is K sub S, and that is the saturated hydraulic conductivity. All right. Now we need to estimate H sub F, my capillary pressure at the wetting front. And we can do that using the Brooks-Corey equation. 2 plus 3 lambda times psi b over 2, 1 plus 3 lambda. All right, so this allows us to estimate the cap pressure at the wetting front for our soil. And we need the Brooks-Corey parameters, psi sub b, the bubble air entry pressure, and lambda that has to do with the pore size distribution. All right. So for any time t, I can calculate tau. I can calculate psi, I can calculate tau, and I can calculate q sub I. And what we'll get is a function. This would be time, and this would be q sub I. And we'll get this infiltration rate. It's going to start off really high, and it's going to converge to a steady state. This is the beginning of the precipitation event, and this is sometime after the precipitation event begins. All right, so that should be good to go. And that's how we calculate infiltration rate. If we wanted to know the total infiltration over a given time, we need to calculate the area under this curve, or integrate the curve. We can do that by calculating this curve and then numerically integrating it, which means just sort of taking little columns of some delta t and adding them together. The smaller those columns get, the closer we get to the true integral. All right, that'll do it for this lecture. Enjoy, and we will talk to you guys later.